Here we have the function f of x equal to x squared plus 4. And we want to find the area of the region bounded by the graph and the x-axis from 0 to 4. And then instead of dividing the interval from 0 to 4 into equal number of sub-intervals, we choose to partition the interval from 0 to 4 as follows. X of 0 will be 0, x of 1 will be 4 times 1 squared divided by n squared, where n is the number of rectangles. And then x of 2 will be 4 times 2 squared divided by n squared. And then x of 3, 4 times 3 squared divided by n squared. And then x of n will be 4 times n squared divided by n squared, which is 4. And so the first must be 0 and the last must be 4. And of course, there's an infinite number of ways to partition this the interval from 0 to 4. And so we just happen to choose this way. But whatever way we choose, the first must be 0 and the last must be 4. And so if this is the pattern, then in general x of I would be 4 times I squared divided by n squared. And so, for example, when n is 8, then x of 0 would be 0, and x of 1 would be 4 times 1 squared divided by a squared, which is 6 over 64. And then x of 2 would be 4 times 2 to the second over a squared, which is 16 over 64. And then x of 3 would be 4 times 3 squared over a squared, which is 36 over 64. And so on. And then x of 4 will be 1, x of 5 will be 100 over 64, and then x of 6 is 144 over 64, x of 7 is 196 over 64, and x of 8 is it'd be just 4. And now let's look at the widths of the rectangles. The width of the first rectangle will be x of 1 minus x of 0, which will be 4 over n squared. Okay, this is x of 1. And then width of the second rectangle will be x of 2 minus x of 1. So it will be this minus, this is x of 2, this is x of 1. And we get 12 over n squared. And so if n were 8, then it would be 12 over 64. And then width of the third rectangle will be x of 3 minus x of 2. And so we'll get 20 over n squared. And again, if n is 64, if n is 8, then it'll be 20 over 64. And then width of the fourth rectangle will be x of 4 minus x of 3. And we get 28 over n squared. Or n, again, is the number of rectangles. And now let's get a general formula for the width of the ith rectangle. And so the width of the ith rectangle would be x of y minus x of y minus 1. And since we chose this pattern right here, then x of y is 4i squared over n squared. And so right here for the x of y, we have 4i squared over n squared. And then x of y minus 1 in the place of I, we just put I minus 1. And this becomes 4i squared, and then I minus 1 squared is I squared minus 2i plus 1. And then multiply this out, we get 4i squared minus 4i squared plus 8i minus 4. 4i squared minus 4i squared is 0, and so what's left is just 8i minus 4 over n squared. And so delta x of y, which is the width of the ith rectangle, will be 8i minus 4 over n squared. And if we look at the widths right here, they are all different. The last one is the largest one. And so let's look at the largest width. for a given partition that's chosen, the largest width is denoted as the double bars with the delta inside, and it's called the norm of the partition. So the norm of the partition is the largest width. And so in this case, if we just have 8 rectangles, and then this would be 4 minus 3.0625. This is 4 and this is x sub 7, which is 3.0625. And that comes out to be 93.75. And so it's called the norm of the partition. And then also note that if we allow the norm or the largest width to approach 0, meaning making it smaller and smaller and smaller, making this largest one right here to become 0, approaching 0, then the only way that would happen if we have an infinite number of rectangles. And so if we allow the norm to approach 0, then the number of subintervals or the number of rectangles will go to infinity. The converse is not true. There are examples where n is approaching infinity, but the norm does not approach 0. And so this way is true. If we allow the norm to approach 0, then n will approach infinity. And now let's find the widths of each rectangle. And so width number 1 will be x of 1 minus x of 0. It will be 0.625. And then width number 2 is x of 2 minus x of 1, so it will be 0.1875, and so on. And so these are the widths of the rectangles. And now let's find the heights of the rectangles. For the first subinterval, which runs from 0 to 0.625. So the first interval is from 0 to 0.0625. And we want to use the right endpoint method. And therefore we will use the 0.0625 to find the height of the first rectangle. And so the height, that's just to find the x, to find the y when x is 0.625. And so it would be f of 0.625, and that comes out to be 4.0039. And so the height of the first rectangle would be 4.039. The second rectangle is from the interval from 0, this right here, this is 0.0625, and this right here is 0.25. And again, we're using the right endpoint method, and therefore we will use the 0.25 to find the height of the second rectangle. And so when x is 0.25, y is 4.0625. And so this point right here is the point 0.25 for the x and 4.0625 for the y. And that would be the height of the second rectangle. And then so on, similarly for the other 6 rectangles, these are the heights of the other rectangles. And let's just do the last one, which is the 8th rectangle. This right here is 3.0625, and this is 4. And we will use the 4, which is the right endpoint, to find the height of the 8th rectangle. And so f of 4 is 20. And so the height of the last rectangle is 20. And so now that we have found the widths of the rectangles and the heights of the rectangles, and then these are the areas of the rectangles. And again, here if we add them up, then we get 44.022. But we notice that the 8 rectangles that we use with the right endpoint method, the rectangles, they are outside of the shaded region, and therefore this number right here, it would be larger than the actual shaded region. And so to get the exact area of the shaded region, what we need to do is allow the number of rectangles to approach infinity, meaning allow the norm or the largest width to go to 0, and then that will allow the number of rectangles to go to 0. Allow the let me say that again. That will allow the number of rectangles to go to infinity. And so now let's fill this up with more rectangles instead of just 8. Here's filling the shaded region with 20 rectangles. And we get an area of 39.94 for the sum of areas of the rectangles. Now let's fill it up with 50. And that's 50 rectangles. And the last rectangle still has the largest width. And then now let's fill it up with 100. And these are the exabytes. And we get 37.84. And then now let's go fill this shaded region here up with an infinite number of rectangles. So we have chosen to partition the interval from 0 to 4 this way. And therefore exabyte is 4i squared over n squared. And then we also found the formula for the width of the ith rectangle is 8i minus 4 over n squared. So once again, the function we're dealing with is x squared plus 4, and this is exabyte, and this is the width of the ith rectangle. So now let's find the height of the ith rectangle. And so the height of the ith rectangle will be f of exabyte. But exabyte is 4i squared over n squared. And then we get square, since this is x squared plus 4. So in the place of x, we put exabyte, which is this, and then plus 4. And this quantity becomes 16i to the 4th, dividing by n to the 4th. And now let's get a common denominator, so multiply 4 by n to the 4th, dividing by n to the 4th. And then now we have a common denominator of n to the 4th. So the top would just be 16i to the 4th plus 4n to the 4th. So this is the height of the ith rectangle using the right endpoint method. And now let's get the area of the ith rectangle. So it would be the height times the width. Once again, this is the width of ith rectangle. And so it would be this quantity times 8i minus 4 over n squared. The bottom is n to the 4th times n to the 2nd, which is n to the 6th. And then the top, which is multiplied out, and we get 128i to the 5th minus 64i to the 4th plus 32i times n to the 4th and minus 16 n to the 4th. So this is the area of the ith rectangle in terms of n. And now let's find the areas of n number of rectangles. And so this is the sum of areas of n rectangles. And so we just do summation from 1 to n. And then now let's separate these numbers right here. So it'll be 128 over I to the 5th dividing by n to the 6th, which is what we have right here. And then the I to the 5th, which is I to the 5th. And recall that summation of sum is just sum of summation. Summation of difference is just difference of summation. So that's why we can separate them like this. And then 64 I to the fourth divided by n to the sixth. Then we have 64 over n to the sixth. And then times summation of I to the fourth. And then this is 32I n to the fourth dividing by n to the sixth. When we do n to the fourth divided by n to the sixth, we have n to the second in the denominator. And then 32 is 32, and then here we have the I. And then the last term we have 16 n to the fourth dividing by n to the sixth, then we get 16 over n squared. And so next, we need a formula for summation of I to the fifth. We need a formula for summation of I to the fourth, and then summation of I. And this is the term 16 over n squared. There's no I. So we could think of it as constant, because this is the summation is with respect to I. And recall that if we have a summation of a constant, then it'd be just the constant times n. And so this last summation right here would be just 16 over n squared times n. And then the formulas for I is n squared over 2 plus n over 2. And then for summation of I to the fourth and the fifth, we have this formula. And then for I to the fifth is this formula. In the place of summation of I to the fifth, we have 1/6 n to the sixth plus 1/2 n to the fifth plus 5/12 n to the fourth minus 1/12 n squared. In the place of summation of I to the fourth, we have 1/5 n to the fifth plus 1/2 n to the fourth plus 1/3 n to the third and minus 1/30th n. And then the last one we need is summation of I, which is n squared over 2 plus n over 2. And then multiply this out. This is what we get for the first line. And then multiply all of this out, then we'll get the second line. And then last, we'll get this line right here. And so this is the sum of areas of n number of rectangles. But we want the exact area, and so we need to allow n to run to infinity or allow the norm, the largest width, to run to 0, to approach 0. And so allowing the norm or the largest width to run to 0, that will allow n, the number of subintervals or the number of rectangles, to run to infinity. So as n runs to infinity, then we get 128 over 6. This term will go to 0 since n runs to infinity. This will go to 0, 0, 0, 0, 0, and 0. And then we get 16. And then this term will go to 0, and that will go to 0. And so the answer will be 128 over 6 plus 16, which is 37 1/3. And so which leads us to the, so this right here, this is a limit quantity. When this limit does exist, then we denote it as the definite integral. So this is called the definite integral from a to b. In this case, a will be 0, b will be 4. Because that's what the shaded region is. It's from 0 to 4. And then f of x is x squared plus 4. And then times the differential of x. And so this is called the definite integral. And it represents the this limit quantity. So this limit quantity is a number, is a value. So whatever that is, in this case it turns out to be 37 and 1/3. And therefore this definite integral right here is equal to 37 and 1/3. And it represents the area between the graph and the axis. So this is called a definite integral. And in summary, the area of the shaded region, the exact area is 37 and 1/3. And is denoted as the limit as the norm goes to 0, which is also defined as the definite integral from 0 to 4 of x squared plus 4 times dx. And so the exact area is 37 and 1/3. Earlier when we did fill this up with the 100 rectangles, we got 37.84, which is close to the close to the 37 and 1/3.